Deep beneath the global oceans, a vast physical network of cables carries the world's digital information. This critical infrastructure begins its journey here, inside a specialized factory designed to produce continuous lengths. The core component starts as a synthetic glass preform, a silica cylinder with precise optical properties. This preform is hoisted to the top of a drawing tower and lowered into a high-temperature furnace. Gravity assists as a single, hair-thin fiber is drawn from the melting tip of the glass rod. Laser micrometers measure the fiber diameter thousands of times per second to ensure it remains perfectly uniform. A liquid acrylic coating is immediately applied to the glass to protect it from moisture and abrasion. Ultraviolet lamps cure the coating instantly, hardening the protective layer before the fiber touches any solid surface. The finished optical fiber is wound onto large take-up spools, ready for the rigorous proof testing phase. Every inch of fiber is stretched to a specific tension to ensure it will survive deployment stress. To identify individual strands within a cable, the clear fibers are run through a high-speed coloring machine.
UV curable ink is applied, giving each strand a distinct color code for engineers to identify later.
The colored fibers are grouped together, often in bundles of 12, to prepare for the tube extrusion. The fiber bundle enters an extruder, where a plastic buffer tube is formed around the glass strands. A thixotropic jelly is injected into the tube, cushioning the fibers and preventing water ingress if breached. The hot plastic tube travels through a long water trough, cooling and hardening into a protective shell. Spools of fiber-filled buffer tubes are loaded onto a stranding machine to build the cable's central core. A high-strength steel king wire is fed into the center, providing the primary tensile strength for the cable. The machine rotates, wrapping the plastic buffer tubes helically around the central steel wire to provide flexibility. Water-blocking tape is wound around the bundle to hold the tubes in place and seal out moisture.
The optical core now moves to the sheathing line, where it will be encased in a copper conductor.
A continuous strip of flat copper is fed from a coil, running parallel beneath the optical fiber core. Precision rollers gradually bend the copper strip upwards, forming a tube that completely encases the fiber unit.
A tungsten inert gas torch welds the longitudinal seam, creating a hermetically sealed, conductive copper tube. The tube passes through a reduction die, shrinking the copper diameter to grip the internal core tightly.
This copper layer carries the high-voltage power needed to amplify the light signals across the ocean floor.
Polyethylene pellets are melted down to create the insulation layer that separates the conductor from the water.
A thick layer of polyethylene is extruded over the copper, forming the dielectric barrier of the cable.
X-ray sensors continuously monitor the thickness of the plastic to ensure perfect concentricity around the conductor.
The cable enters an extremely long cooling trough, gradually lowering the temperature to prevent internal stress fractures.
This stage produces lightweight cable, used in the deep ocean where the risk of damage is minimal. For shallower waters, the cable requires additional protection in the form of high-tensile steel wire armor.
The lightweight core is fed through the center of a rotating cage holding large bobbins of steel wire. Thick steel wires are wrapped helically around the polyethylene core to provide mechanical protection against ship anchors.
The steel armor is immediately coated in hot bitumen to prevent corrosion from the harsh saltwater environment.
Layers of polypropylene yarn are wound over the sticky bitumen to create a handleable outer surface.
For rocky seabeds, a second layer of steel armor is applied, doubling the weight and protection level.
The outer yarn is often applied in a distinctive black and white pattern to improve visibility underwater. Samples undergo high-voltage testing to ensure the insulation can withstand the 10,000 volts required for power.
Optical engineers use reflectometers to verify there are no breaks or signal attenuation within the glass fibers.
Signal amplifiers, known as repeaters, must be spliced into the cable every 50 to 100 kilometers. In a clean room, technicians strip back the armoring and insulation to expose the delicate optical fibers. A fusion splicer uses an electric arc to melt the glass ends together, creating a seamless optical connection. The splice is X-rayed to ensure there are no bubbles or misalignments that could cause signal loss.
The spliced area is overmolded with polyethylene, restoring the insulation integrity of the continuous cable line.
The delicate optics are housed inside a beryllium copper pressure vessel designed to withstand crushing ocean depths. The finished cable travels along an extensive overhead gantry system towards the massive storage tanks. The cable is lowered into enormous circular tanks, where it is manually coiled by a team of workers.
Workers walk in continuous circles, carefully layering the cable to prevent tangles during the rapid deployment phase.
A single storage tank can hold thousands of kilometers of continuous cable, waiting for the arrival of the ship.
When the cable ship arrives, it docks adjacent to the factory to begin the lengthy loading process. The cable is pulled from the tanks and runs along a specialized track known as the cable highway.
It traverses the series of towers and pulleys, bridging the gap between the manufacturing floor and the vessel.
The cable enters the stern of the ship, where linear cable engines control the speed of the intake.
Inside the ship's hold, another team of coilers repeats the stacking process, filling the vessel's massive tanks. When a repeater reaches the ship, cranes gently lift the heavy amplifier unit to bypass the standard pulleys. Loading a transoceanic cable system is a slow operation that can take several weeks of continuous running. Once fully loaded, the cable ship departs for the open ocean to begin the precise installation process.
For shallow waters, a massive sea plow is used to bury the cable beneath the seabed sediment.
The plow cuts a trench in the ocean floor, laying the cable and covering it to protect against fishing trawlers.
In the deep ocean, the cable is simply paid out from the stern, settling onto the seabed contours.
The ship follows a meticulously surveyed route, avoiding underwater volcanoes, trenches, and shipwrecks. Remote-operated vehicles are deployed to inspect the touchdown point and ensure the cable is not suspended. A suspended cable is under tension and at risk of snapping, so it must lay flat against the bottom. Branching units are deployed to split the signal, allowing one cable system to serve multiple countries. At the destination, the cable end is floated to shore and pulled into a beach manhole. Divers secure the articulated iron pipes that protect the cable as it crosses the turbulent surf zone. Inside the landing station, the optical fibers are connected to the terrestrial backhaul network. Data begins to flow at the speed of light, connecting continents and enabling the global internet. Hundreds of these cables crisscross the planet, forming the invisible nervous system of modern communication. Back at the factory, copper scraps and plastic waste are collected for recycling to minimize environmental impact.
Quality assurance teams rigorously test the outer jacket to ensure it can survive 25 years underwater.
The steel armor wires are pulled to their breaking point to verify they meet the specified tensile strength. Sample segments are placed in hyperbaric chambers to simulate the crushing pressure of the Mariana Trench. Microscopes reveal the integrity of the copper weld,
ensuring no microscopic pinholes exist.
Engineers constantly refine cable designs to increase data capacity and reduce the diameter of the product.
The inventory of optical fiber is carefully managed, as different glass types optimize different wavelengths. Maintenance crews keep the massive extruders cleaning and running, as any downtime delays the entire project.
The cooling water must be kept clean to prevent mineral deposits from contaminating the cable surface.
Raw materials like steel wire arrive in massive coils, which are welded together for continuous feeding.
Operators butt weld the ends of the steel wires, smoothing the joint to prevent snags in the machine.
The bitumen tanks are kept at a constant high temperature to ensure the asphalt flows smoothly.
Powerful ventilation systems extract the fumes from the hot asphalt, maintaining air quality for the workers.
Safety gear is mandatory near the armoring line, where high-speed rotating metal and hot fluids converge.
The cable highway often bridges over public roads to reach the port, a landmark of the coastal town.
If a cable is damaged, specialized repair ships grapple the seabed to retrieve and splice the ends.
Historically, shark bites were a threat, but modern armoring and burial techniques have eliminated this issue.
Today, the biggest threat to these lines comes from fishing trawlers and ships dropping anchors inadvertently. Looking at the cross-section, we see the complex layers engineering designed to protect the fragile glass core. Through this hair-thin glass, terabits of data stream every second, powering the global digital economy. The skill of the factory workforce is the first line of defense against global communication blackouts. Underneath these waters lies a man-made web that has brought the human race closer together. As the demand for data grows, these ships continue to weave new connections across the planet. Back on shore, the factory runs 24 hours a day, extruding the next link in the chain. The mesmerizing cycle of coiling continues, storing potential connectivity in these massive industrial tanks. From a glass rod to an ocean-spanning lifeline, this is the engineering marvel of the submarine cable. This concludes the full industrial process behind the manufacturing of the Internet's physical backbone.
If you enjoyed this deep dive into infrastructure, please subscribe to the channel for more documentaries.
Click the video on the screen to explore how other massive industrial components are manufactured.
Thank you for watching this detailed tour of the submarine cable industry and its technologies.